much, Steve. So I'd like to start off with an observation which may be interested in that the compositions of the atmospheres of the planets that cosmochemically or in their cosmolocation bracket the Earth have very similar present-day CO2 to N2 ratios. So we see that Venus has about 43 and Mars about 55. Curiously, then, we turn to the Earth, which, despite bracketing these, falling within these planets in terms of its total pressure, so 92 bars for Venus and 610 Pascal for Mars, has a distinctly different CO2 to N2 ratio. And so the question then becomes, why did the Earth evolve in such a distinct manner from its planetary neighbors? And before we get started on this question, I'd just like to start off with some nomenclature. We refer to primary atmospheres as those captured around planets from the nebular gas, and therefore they contain largely hydrogen and helium. Whereas the focus of this talk will be largely on the secondary atmospheres, and that is an atmosphere that has been outgassed from the interior of the planet during either a magma ocean stage, as depicted here, or during post-solidification from outgassing of volcanic activity. And so these atmospheres tend to be heavier, containing CO2 and CO species, as well as water. And of course, for the Earth in particular, we then refer to a tertiary atmosphere, which has then been modified by biological activity. So as I mentioned, I'd like to start off with the secondary atmosphere stage of planet formation, and particularly as relevant to the Earth. So why do they matter, you may be asking? And I guess I don't need to convince you of this, and there's people in the audience that have much more extensive information than I do about these processes, but Charles Darwin, of course, predicted that life began in warm little ponds, and this became enumerated in the 1950s at the University of Chicago, notably by Harold Urey and Stanley Miller, of course, in which they advocated a potentially reducing atmosphere composed of methane and ammonia in the presence of a spark discharge, and water would produce a bevy of amino acids, some of which are necessary for life. Question then becomes, did such atmospheres really exist on the early Earth? And to answer this question, we can take some key geochemical evidence that's been known for about 100 years now. And this is a letter to Nature, obviously a very different format to what we have today. But the impact was that there was an abnormal scarcity of the inert gases, i.e. the noble gases that had been observed by looking at the abundances of these elements in the Earth. And that has been confirmed subsequently in these more recent studies, in which what we show here is that relative to the solar composition, which we plot here at 1, there are a large depletion of these so-called noble gases, which do not participate readily in chemical reactions. And so this is, of course, relative to the more reactive, yet similarly volatile elements such as hydrogen and nitrogen. And so this observation is really taken to mean that the Earth had lost its primary atmosphere, which would contain a lot of these noble gases, and it was subsequently replaced by an atmosphere that was outgassed from its interior. Now, as Steve mentioned earlier on, that there is a key event which occurred in the lifetime of the Earth, and that is the moon forming giant impact. And as mentioned, this impact deposits enough energy to cause wholesale melting of the Earth's mantle. And so this temperature increase can be estimated given the heat capacity of rock. And it turns out that the temperature increase is of the order of about 6,000 Kelvin. And so this means, because the liquidus temperature of peridotite, i.e. the rock that forms the bulk of the Earth's mantle, is about 2,000 Kelvin or slightly above, we're able to not only melt the mantle, but also vaporize a significant quantity of rock at the same time. Then the question that is relevant for our thesis here is whether such a vaporized atmosphere was indeed reduced as envisaged by Miller and Urey, or whether it contains more oxidized species such as CO2 and H2O. Now, we can use a thermodynamic expression or identity here to give us a better clue as to what atmosphere really existed. And this is because we have very little trace of the early atmosphere today, but we can use the rock record as an indirect tracer of what occurred. And this is because the oxygen fugacity recorded in mantle rocks should be at equilibrium equal to that present in an early atmosphere. So the question, then the sort of the reaction that we can use to constrain this behavior is the ratio of reduced iron, Fe2+, to oxidized iron, Fe3+, because they are related by the fugacity, or in an ideal gas, the partial pressure of oxygen. And we do have expressions to relate these two quantities, but these expressions are really only determined for basaltic melts. And so these are the type of magmas that are produced on Earth today. However, if the whole Earth was molten at some stage post-moon-forming giant impact, then we would no longer have a basalt, but we would have a liquid peridotite. And just to illustrate how poorly these models that are based on basaltic rocks work for peridotite, I show this figure here, which is for a constant ratio of iron 3+ to iron 2+, here taken to be 3.7%, and a constant temperature. Existing models are shown as these vertical lines here. And so you can see that the oxygen fugacity that these models predict has a range of about 6 orders of magnitude, which means that with existing formulations, we may predict an atmosphere which is rich in CO and H2O, or we may predict an atmosphere which is rich in CO2 and H2O. So the aim of this work is really to provide a calibration for a realistic Earth-like composition that is peridotite at the magma ocean stage, and therefore constrain whether we had CO2 and H2O or whether we had CO and H2. And to do this, we use a sort of a new apparatus, which I can show you a video of here, known as an aerodynamic laser levitation furnace, in which essentially we mix up oxides in approximately peridotite proportions, and that composition is shown here in weight percent. And then sort of heat them up together, cook them up together in different gas streams, which we control by varying the flow rates of CO2 and H2 in the atmosphere surrounding our miniature Earth. And with this, we can explore a range of possible oxygen fugacities in the atmosphere. And so I'll just show you how this works. We have our system here, and it's heated by a CO2 laser at 10.6 microns. And you can see here the temperature we achieve is in excess of 1900 degrees Celsius in our floating Earth. And once we've reached equilibrium, about 30 seconds, we can quench the experiment by shutting off the laser power, thereby preserving the high temperature state of the liquid peridotite in the form of a glass, which is, you can see here on the screen. So the next step then is to analyze the iron 3+ to 2+ ratio in these glasses, which we can do by synchrotron techniques. I'll just gloss over this. We have a calibration which we use, which is based on independent measurements by Mössbauer spectroscopy. And you can see that the calibrant glasses in black follow the same trend as our unknowns in green, and therefore we can use this the values of the black points to then calibrate and determine the Fe3+ 2+ ratio in the peridotites. And this uncertainty is relatively small, about 1.5%. So when we do this, we need to we can plot the results up in terms of the stoichiometry of the reaction, which is as I recall here, proportional to the oxygen fugacity to the power of 1/4. And so this is indeed, if we plot the logarithm of the iron 3+ to 2+ ratio of the glass relative to the oxygen fugacity in our gas atmosphere at which the glasses were synthesized, you see that in fact the slope matches the theoretical prediction of 1/4. Now, in order to make these analyses relevant to the early Earth, we need an estimate for the iron 3+ 2+ ratio of the Earth. And what we do to estimate that is to use a global compilation of peridotites from the present day mantle and recent mantle of the Earth to determine to estimate what we think the iron 3+ 2+ ratio of the magma ocean was. And this is where this figure of 3.7% iron 3+ comes from. Now, clearly, we can use this calibration curve then to read off what the oxygen fugacity of the atmosphere would have been given the iron 3+2+ ratio that we measure in today's mantle. And this allows us to fix the CO2 to CO and the H2O to H2 ratios in the early Earth's atmosphere at this temperature. However, of course, if we want to solve for the atmospheric composition discretely, we need in the system H, C, N, and O, we need three constraints. So the first is the oxygen fugacity, which is given by our Fe3+2+ ratio, but we also need to know the H on C ratio of the atmosphere and the H on N ratio of the atmosphere. And this can be done by considering two factors, which I won't go into detail in here for lack of time, but essentially we need to know estimates for these in the bulk silicate Earth. So again, using these peridotites. And then secondly, how readily these, their predominant gas species at this temperature dissolve into the peridotite liquid. And again, this is something we don't have very good experimental evidence. But we can estimate this, and this is the result if we perform a thermodynamic Gibbs free energy minimization for the composition of the Earth's early atmosphere. And what we see is that at high temperatures, we have mostly CO and CO2. This is because water dissolves, is about 99% dissolved in the magma. It's much more soluble than carbon species. So most of the water is actually dissolved in the magma ocean. And if we treat this as a closed system, then you see that with progressive cooling, which is going from right to left, then we have the precipitation of graphite, which causes a relative increase in the fugacities of CO2 and H2O. And at some point, we also have the precipitation of water from the H2O in the steam. And so if we then examine the low temperature state of an early Earth's atmosphere, we find an incredible kinship between that composition here at low temperatures and that presently observed on Venus today. So we have about 70 bars of CO2 and 2 bars of nitrogen, giving us a CO2 to N2 ratio of about 35, very close to Venus's ratio of about 43, as you may recall. So on this basis, we assert that the composition of the terrestrial atmosphere likely resembled that of Venus initially. We have a caveat here, that is, as the magma ocean cools and crystallizes, perhaps some of the water is expelled. And indeed, for our magma ocean atmosphere, we can compute the H on C ratio in equilibrium with the magma and the oxygen fugacity relative to this iron wüstite buffer. And as I mentioned, it falls in the CO-CO2 field. But if we degas the potential water budget that was stored in the mantle, we can push it from a CO-CO2 regime into an H2-H2O regime, as shown here. So if we degas 100% of the water that was contained in the mantle, that's at 1900 Celsius. And if we then cool it down to 25 degrees, again, the same chemical parameter space in the X and Y axes, you can see that actually these CO2 N2 Venus-like atmosphere stability field is very, very large. And so we would need to degas about 80% of all of Earth's water initially in order to push us out of this CO2 N2 regime and into more CH4 N2 regime. And importantly, we never really reach a regime in which we have CH4 and NH3, at least with the water budgets that we think are present in the Earth today. So we think this is a relatively robust conclusion that the Earth probably had a CO2 N2 atmosphere. So again, this makes sense within our solar neighborhood in which we are bracketed by planets with indeed such an atmosphere. So what happened then on Earth to push us out of that regime that is predicted by magma ocean outgassing? And I would point to physical controls. So the first of which is that atmospheric escape on Earth is limited, given that it receives a lower solar insolation flux than Venus and is about the same size. And thank you, Steve. And it's larger than Mars, which means that it is more likely to retain its atmosphere. And this is indeed borne out in the deuterium to hydrogen ratio, which states that Venus lost most of its water, or almost all of it, Mars some fraction, and Earth less than either of them. And so this is a key result of the Earth's particular location and size. And then water, having the stability of liquid water on the surface for long periods of time is important for the for the simple fact that it allows the Urey reaction to take place, in which CO2 is dissolved into water and then can participate in weathering, and therefore CO2 drawdown over time. And so this was modeled by SLEEP about 20 years ago, Norm SLEEP, and showed that this reaction and reactions of this nature, so instead of calcium, you see these different curves relate to a different component such as magnesium. This can occur over about 100 million year timescales, and it leaves us with partial pressures of CO2 of the order of 0.01 bar. So this seems to be an efficient mechanism which is required to have water on the surface. And so here I'd just like to finish off just a note that CO2 into atmospheres are thought to be very inefficient in synthesizing amino acids, but more recent work showed that in the presence of calcium carbonate and at relatively high pHs, you can get significant quantities of these amino acids, even though the yields are slightly lower than that in reduced atmospheres. So perhaps Darwin's idea wasn't so strange after all. So thank you very much.